at double integrals in polar form. So I'm picking a pretty standard question to set it up. In this particular case, they call this a ring. You can see it's from a radius of 1 to 8. So even although this is not to scale, we get the gist of it. So here is going to be 1 and here's going to be 8. And the function that we're going to be doing a double integral of is this one. So in this particular question then, our double integral, we'll call this region D. If you explain or describe this disk shape, you'll have theta, the angle, goes from 0 to 2 pi, agreed? And the radius in this case has an inside radius of 1 and an outside radius of 8. Are we comfortable with how that region got described in terms of polar? Does that seem reasonable? So what you can do here is you can do theta equals 0 to this case 2 pi, r equals 1 to r equals, what was it, 8. And then this fella here, if you remember, in polar form, x is r cos theta, and that y equals r sine theta. And to save some time, won't x squared plus y squared be r squared cos squared theta plus r squared sine squared theta? If you pull out the r squared as a common factor, don't you just get r squared then? Because cos squared plus sine squared. And it's quite helpful.
Under the square root, then you just get r.
Exactly. So it's quite helpful to just remember, because have you noticed there are quite a few questions at x squared plus r squared in it somewhere? Right. So what we've got now is square root of r squared times, and I'm doing a deliberate mistake here. What is missing from my double integral formula in polar form?
It needs to be r d theta.
Right. Now that is r, like you said, right? And this is another r. So basically, aren't we going to be integrating r squared? And whenever possible, have a look to see if you can separate them. And would you agree this one separates? So I'm going to do an integral with respect to theta. And then a different integral with respect to r. Okay, just to remind you, make sure we've got this. When there isn't any theta at all, what do you get where my finger is? What do you replace this here, this space?
1.
1. Okay, and at this point, I'm doing my usual ... Can't you just find these integrals and multiply them and you've got your answer? Now, since I've got this shape in front of me, I want to try and get some mileage out of it and pretend that we had some different shapes. And the first one's going to look like this. Right, imagine that's imagine that's basically the top half of that shape. What would be the limits of integration of theta and r in this story?
0 to pi.
Agreed.
Wait, sorry, theta is 0 to pi.
Yeah, yes. And would you agree the 1 to 8 is the same in both cases? Now, I think we did one like this yesterday, but I want to do one more where it's orientated this way.
Theta is negative pi halves to pi halves, and r is still 1 to 8.
Do you all feel comfortable about quarter shapes and half shapes and orientations and so on, right? So I'm not going to go through them, but couldn't I do a bottom half version of this, which would be what, pi to 2 pi? Couldn't I do a left-hand version of this? In fact, if I did a left-hand version of this, wouldn't the answer be positive pi upon 2 to positive 3/2 pi? Are we good? What would it be if it was the bottom half?
Pi to 2 pi.
Pi to 2 pi. Pi here, 2 pi here. Nailed it, Tessa. So, you know, you sometimes, to me, I need to see pictures of things to get an idea of, you know, in this case, it's mostly the theta issue, isn't it? And in most of these bits of circles, isn't it a theta issue? Don't the R values tend to not be, the only one I can think of is, remember that horrible petal one that we had to do? That one had an R issue as well, because the R value was actually a function of theta. But that's not as common as a bit of a circle one. So let's move on and see what we've got. I'm not going to do all of this one, but I'll just set it up. It's a version of question 9. Oops, question 9. What we have here is a plane, 4x plus y plus z. It's basically a flat piece of paper. And the guy that we've got is a complete circle. So I have no problems, and hopefully you won't have either, that when it's a complete circle, in this case, with radius 1, isn't that the D, right? Whole circles are easy. Now, this guy here should go there, right? So when you set up your double integral, what will you write here?
That would be the 8 minus 4x minus y.
Are you happy about the 4x and the y being converted to r cos's and r sines, right? And then you do your r dr d theta guy and off you go and do it, right? This one does not separate. I'm pretty sure of that. So you're just going to have to do it the old fashioned way. Oh, since these are both numbers, couldn't you do the thetas before the r's or the r's before thetas? Can you switch the order because they're both numbers? Can you imagine it might be less work to do the thetas first and the r second? Right, imagine that might actually help. So you are in charge of order of calculation. Now this one I'm going to set up as well, but not actually do any more than that. This time, we have a sphere, which is what that guy is. And we have a cylinder that looks like that. This is the D. So I'm going to totally annihilate this thing. I can imagine it, I just can't draw it. Can you imagine on the floor x squared plus y squared? Can you imagine outside that a sphere? Can you imagine someone going up and down? Aren't you going to basically have an entire cylinder with a little curved bit at the top formed by the circle and a little curved circle bit at the bottom? Can you see that your double integral in this case would probably look something like this if you separated it? There would be a cylinder with a curved top and a curved bottom. So you would be finding, the double integral would be finding that. Does that make sense to you? Right. Now, we need to take this and rewrite it as z squared equals 36 take away x squared take away y squared. And that's going to be z equals the square root of 36 take away x squared take away y squared. And then finally, won't this z have to be converted into r's and thetas? Right, let's make this guy. Do you recognize that negative x squared, negative y squared gets you negative r squared? Do you need to see the line in that, or can you imagine it in your brain? Negative x squared, negative y squared is the same as negative r squared when you're finished.
Yeah, because you can factor out the negative and then you'd get the sine squared in the and the y squared.
Right. So in this integral, your double integral is going to be just a basic circle, right? So it's going to be 0 to 2 pi, and it's going to be, what's the radius, 1 here? So 0 to 1. And isn't your function going to be 36 take away r squared? And then you do an r dr d theta. Are you happy about how that gets set up? Right. This one separates. In fact, doesn't the theta just become a 1? How are you going to integrate the square root of 36 take away r squared times r dr using Calc 2 tricks?
That would be our good friend the u sub. Just remember that we have that negative.
Yep, and the u would be 36 minus r squared, agreed? And off you go and you do it. We're getting close to the end of these. I'm trying to think which one I want to do. I'll do one like 11. I might actually do one like 12 because they are different enough to make a difference. We have got question 11, and it's a double integral of x equals 0 to x equals 9, and it's got y equals 0 to y equals the square root of 81 take away x squared, and the function is going to be that guy, obviously dy and dx. Now this integral has been set up to do it the normal dx dy technique, right? But we're going to convert it to polar, because if you try to do that integral the way it's written, can you trust me, nothing good comes out of it, right? It's just not really practical. Now, creating what the disk looks like, or what the shape, I'm telling you can have already what it looks like. Y goes from 0 to this thing, and x goes from 0 to 9, right? So I'm going to focus on what does this curve look like? Well, if you square both sides, and then you add an x squared to both sides, do you see it was just a hidden circle radius 9? Are we good so far? Hidden circle. Now I'm going to draw the whole circle in, even although I know the shape isn't going to be the whole thing. Now you tell me that y goes from 0 to this guy, okay? Now if I tell you y goes from 0 to this guy, aren't you basically saying this half? So far so good. Now if you tell me x goes from 0 to 9, so x goes from 0 to 9, aren't you also telling me that it's this half, or this piece? So the combination of the information that's given here and the information that's given here, do you see it generates that little corner? And so we know that the r value is going to be from 0 to 9, but the theta value is only going to be from 0 to pi upon 2. Are you comfortable with what I just created there? Now, that guy there, the minus x squared minus y squared, isn't he going to turn into something nicer?
So why exactly are we only doing a quarter of the quadrant?
I didn't.
The first quadrant?
Because x is going from 0 to 9. So since x is 0 and this is 9, the shape only exists from here to here. So it's only this quadrant.
Oh, because it's only positive 1.
Yeah, if this had said negative 9 to 9, I would have kept the top half. Right. Okay, back to this guy. What does negative x squared, negative y squared simplify down to using r's and thetas?
Minus r squared.
Great. Aren't you going to get an r dr d theta guy? And then you put the limits integration in. Would you agree that is a separable situation again, where the theta is just going to be a 1 d theta? And in Calc 2, because this is Calc 2 now, how do you integrate this e to the negative r squared times r?
Negative e to the negative r squared. You basically just bring down a negative 1.
No.
No, I did. Okay,
No.
I did this yesterday, and I did
Right.
a u sub.
Yeah, that's it. You do a u sub. And the u sub will be negative r squared, or if you like r squared, both work. So it'd be a u sub using r squared, or a version of it. And that's as much as I'll do with that one.
That was actually, so with the exception of converting everything, to
Is it
pull
quite
another
nice?
operation, it's kind of like one of those examples that we did yesterday with the e to the negative r.
Yeah. I mean, I guess polar has quite a restrictive use. Would you agree you would only do polar if the shape was very, I called it circular, right? Like it's a bit of circle, right? Polar will probably work quite well in those situations. Would you agree you wouldn't try and use polar if it was a banana shape, right? An x squared and a square root of x, right? You wouldn't try and use polar on those because those just don't play well, right? The algebra is not nice. So it's a niche market, right? Polar should only really be used when you see the region D is a bit of a circle, or maybe one of those little leaves of a, one of those little flower shaped things, right? Where R is 8 cosine 3 theta, that kind of shape, right? You could do it in those cases as well. And so the last one, and then we're moving on, is question 12. And the integral is x equals 0 to x equals 2, and y equals 0 to y equals the square root of 2 take away, oh yeah, worse than that, 2x take away x squared. And then it's going to be a 9, this guy, and dy dx. Whoa. Right, first thing first, we have got to figure out what this information is giving me. Now, I'm going to take the only bit that's not a number, because that's got the curve, and we got this. If I square both sides, we get that. If I add an x squared to both sides and take away 2x, we get that. And I am not happy. I can tell you that that's a circle whose center is not the origin. In fact, I can tell you that's a circle. Well, let's just show you. I'm about to do it in Desmos, but I'm going to just show you in algebra. If you call that x minus 1 squared, you have to subtract another 1. So I've basically done completing the square. I don't know how many years ago you've done that. If you add 1 to both sides, can you see a circle whose center is 1, 0 and whose radius is 1? Do you see that, guys? Right, now, if I go to here and I put a center at 1, 0, and I draw a circle whose radius is meant to be 1, and we'll pretend this is 1. So I guess that gets me to 0, right? That gets me 2, and there's 1 in the middle. I've got this shape. If you do x equals 0 to x equals 2, so x equals 0 to x equals 2, and the fact that that's positive, doesn't that mean that the shape we're interested in is that half circle? Now, things are going to get messy. We are going to try and draw this shape. The theta, I think I can argue. Would you agree that if we do what are basically called radial lines, right? Would you agree that theta equals 0 gets you to here, right? And then as the radial lines go down, you're going to have to trust me, but isn't there one at the end which is essentially vertical? Are you happy with theta going from 0 to pi upon 2? Right. Now, the hard one is, what the heck does y do? Sorry, what the heck the radius does. Now, the radius is going to have to come somehow out of this. So I'm going to go on the side that I recognize. Would you agree that when you get to this point, won't the radius be 0? Now, if I do any radial line, won't the other value of the radius be this guy? And how do I get this guy? I get him by using this. Okay, this is not going to end well. Let me just do something here to make sure I don't screw up. So I'll have a solution to compare it against. Right. Well, you tell me, what is y equal to when you convert it into polar form? What is y equal to?
2r cosine minus 2r squared cosine squared.
Oh, you're doing this side. Okay. So r sine theta, that's the y, is equal to what you just said. 2 cosine theta, not 2 r cosine theta. Take away r cosine theta squared. Are you with me so far? Now, somehow or other, I want this to be r equals a function of theta. And once I find that, I'm putting it there. And I've already got the thing set up. So I am ready to take this guy to time. There is something. Oh, there's a 9 there. Okay. This, I just had a look at the answer. Not how they did it, but evidently, this thing's going to be equal to r equals 2 times the cosine of theta. So at least now I know what I'm heading for. I can't see that yet, but evidently, that's what it's going to be. How on earth does that guy, which is basically this, become that guy? Well, I'll try. R sine theta, 2r. I like questions I've never seen before. I got that guy. What did I do?
Square both sides.
Okay, that sounds like a good start. That's a minus, by the way. And can I add that to both sides? You still with me? Can you see what's going to happen next? What's happening here? What does that become?
R
The
squared.
left side becomes 1, it's a trig identity.
Right, and r squared times 1, you get that. So we're now looking at this. Technically speaking, couldn't I divide both sides by r? Bearing in mind that I'm not going to do it when r is 0, but since I've already included r equals 0, I can get away with that. Can you now see? Wow, is that not amazing? That such an ugly looking thing ends up being r equals 2 cosine theta. That's why the guys who write textbooks get all the big bucks. I could not have created that, right, this thing, and expected something pretty to come out of it. If you randomly pick things, isn't there a good chance that would turn into some really ugly looking expressions? Well, now you know everything. You can say, well, which one do I do first? Is this going to be the r guy or the theta guy?
It should be r because then we'll have another theta.
Correct. And then the theta is what we've decided from 0 to pi upon 2. Didn't we agree on that already? And now what do we have? We have a function here. Where's the function? I've lost it. It's 9 of these guys. Doesn't that just become 9r times r dr d theta? Are we comfortable with that? So it's going to be the integral from r equals 0 to 2 cosine theta of 9r squared dr. And then after that, we'll do the thetas. Well, Add 1 to the power, divide by the new power, you get 3r cubed, evaluated at 0 and 2 cosines. It's pi upon 2, not 2 pi. So what's that going to look like? That's going to look like 3 times 2 cosine thetas cubed. Take away 3 times nothing, take away nothing, right? So I'm going to get 24 cos cubes. Evaluated from 0 to half pi. Okay, this is Calc 2 again. Tell me the technique for integrating cos cubed.
U sub,
Interesting.
and then you have U just be cosine.
Oh,
So we don't have a sign to be able to do it.
well, let's see if we can work on that. And I'm going to rewrite this. That's meant to be 24, by the way, as a cosine theta times a cosine squared theta. Because someone mentioned we don't have a sine theta, didn't they?
You
And-
swap the trig identity out
Okay.
for 1 minus sine theta or sine squared theta.
You nailed it. Now that I've rewritten it this way, do you want to change your mind about who the U sub is?
It would be the 1 minus sine squared theta.
No, not as much
Oh.
as that.
No, it would still be cosine.
No. What would do it? You keep, I mean, it's like you're bouncing left and right. You're almost there. You're just not
Sine
hitting the
squared
middle
theta.
here. No. Just, I think I've heard everything except the only thing that's left. So if you
Just
tell me
sine.
the only, it's going to be the sine theta. And can you trust me if you do a U equals sine theta as your U sub, that thing will 24, that'll disappear and you'll end up with that guy. And so that's easy to do, right? If you did any of the other ones, there'd be a problem. If I did U equals cos theta, wouldn't I generate a sine theta? But you see, sine theta doesn't play well with that. You wouldn't get rid of it. You'd have a bit that you couldn't fix. If you did 1 minus sine squared as a U sub, or just sine squared as a U sub, do you know you're going to get 2 sine theta cosine theta, in which case you're in the same boat, right? You've got a bit left over that you can't get rid of. Whereas if you do sine theta, isn't its derivative cosine, and all you're left with is 1 minus sine squared, which gets you the 1 minus U squared. So you know it's a U sub, so I guess what happens is you try that one, yeah, never worked. You try the next one, yeah, never worked, right? But eventually, isn't there a choice? Not a guaranteed rule, but most of the time, isn't the U sub in these questions a single sine theta or a single cosine theta, right? If you go back and you look at your notes from Calc 2, you tend to only do single sines and single cosines in these types of questions. And basically, that would be the end of that question. So we have found, I hope, how to find double integrals in polar form for the subgroup of questions where the region, the D, is some kind of circle, right? Something to do with a circle, I guess. Any questions before we move on to the next section, which is 15.4? Feel comfortable about this? Right, I'm just setting the thing up right now. If you can wait, 15.4. There we go. Right, let's try and that's what I'm looking for. Can you remember Calc 2? And we looked at applications of Calc 2. For instance, couldn't you find the volume of revolution using integrals? What else could you do? Couldn't you get the average value of a function using integrals? Actually, we've done that application. But there are other things, right? Couldn't you get the area under a curve, right? So what are the kind of applications that you can do using, say, double integrals? Well, you can find the volume of things. In fact, haven't we done a lot of that? Less so, although we did do one. Can't you get the area of something by just making z equals 1? So you have a guy in the floor and you just make it go up to a height of 1. So won't that number be the area of D, right? So you can use it to find the area of your disk. And you can use this to find the volume of your solid above your disk. We can also use it. I don't know if they do it here, but they probably do. Let's see. Got it. Right. They do it here. We're going to find the center of mass. So we can use double integrals to do that. Center of mass, I have a good feeling about. I know what a center of mass is. The next thing, I guess because I'm not an engineer, I've really never quite figured out what it is. But these things called moments. Has anybody got the Cliff Notes version of what a moment is?
I don't, but I'm sure if I asked my mom, she'd be able to tell me.
Okay. Evidently, engineers want to find things called moments. I know what a center of mass is, right? Can you imagine a center of mass is if you have an object, it's the kind of the center of where it would balance, right? I kind of get a good feeling for what a center of mass does, but what on earth a moment does, I do not know. But evidently, it's very useful thing to know. Just finding the notation, because I couldn't remember what they call it. They call them ix and iy, and the center of mass is called x bar y bar, right? Which is kind of what you'd expect.
I actually, yeah, I just Googled it for you.
Right, tell me what it means, or what, and hopefully it means something I could understand. Because sometimes you look it up and then you have to look up what the words that they used mean as well. So what does it say?
So, and this is from the MIT website.
Cool.
So it says, a moment of a force is a measure of its tendency to cause a body to rotate about a specific point or axis. This is different from the tendency for a body to move or translate in the direction of the force. In order for a moment to develop, the force must act upon the body in such a manner that the body would begin to twist.
Ooh. So it's a special kind of force that is a kind of rotational force that might make an object twist. I guess that would be important.
May I add the Britannica.com portion from that?
Yes.
Moment of inertia. Quantitative measure of the opposition that the body exhibits to having its speed of rotation around an axis altered by the application of a torque, a turning force.
Oh, so moments would probably be important in engines because they are measuring some kind of force of not wanting to turn or how much you need to make it turn.
Well, it's also going to have applications in things like, say, designing blades for windmills, wind turbines.
Yeah. Okay. I got a little bit better understanding. So we want to find these things out. Well, let's cross off some of the applications that have already happened. Aren't most of the double integrals we are doing would be the volume of a solid above a region D? right? So if you have a region D and the function Z is the surface that's on the top, when you do the double integral, you're essentially one way of looking at it is you've essentially found the volume of that object. Can you remember that funny rectangle with the bumps? I don't have it here, but can you remember the guy that looked like this with a little bump at the top? It was basically a cylinder that had a piece of a circle in the top and the bottom. You're finding volumes. So the guys we're going to focus on then are going to be these two applications in particular. So. Oh, I just saw one that I didn't even see because I'm not an engineer. We are going to find cumulative charge. Okay. You have, this is the first question, and you have a rectangle. So the x's go from 0 to 8 in this question, and the y's go from 3 to 9. So imagine this is the floor. And you have a rectangle, x is 0 to 8, and let's pretend that's 3 and that's 9. So you've got this guy. And on this metal plate, there is a charge density function called sigma. And so at any given point, the amount of charge is described by 4 times the x plus, I'll make that different, 6 times the y. So could you imagine that up here, that's a bad color, that up here, there's a lot of charge, and down here, there's not quite as much. And so can you imagine a shape, a piece of metal, where there's a variable charge on it, right? For whatever reason, a lot more charge on one piece of it and less on the other. But what you want to do is find the cumulative charge. And the cumulative charge is described as a double integral of this fella here. I guess I'll call it sigma, because that's what they're calling it. Sigma xy dA. So if you have a function that represents, I don't know if you can do this, but can you imagine a plate where at any given point there was a different amount of magnetic field on it? So some had stronger magnetic field than others. Then if you did this, wouldn't you get the cumulative magnetic field? How much in total there was in the entire plate, right? So if you want to find something that uses the word cumulative charge, I don't know, cumulative magnetism, cumulative insert engineered word here, you basically do a double integral of the plate with respect to the charge function. So in this case, it's going to be from x equals 0 to x equals 8, from y equals 3 to y equals 9, of a 4x plus a 6y, and I'm doing it as a dy dx. Are we comfortable with that integral? Would you be able to integrate it and feel comfortable about the answer? Or do you want me to go further?
I'm good.
You're good, right? So can I just do my classic ... and pretend the answer is 42? Why is the answer to many questions that I do 42?
Because it's the answer to life, the universe, and everything.
Well done. She knows the context. Does anybody know the context like Sally does? Where does that come from?
I know it from a Japanese context. So 4 and 2, if you pronounce them in Japanese, it's the word death.
I did not know that. So that is not a good that's not a good number to have in your door then, right? Your house.
Probably not.
Or hotel room.
Right. If you're 41, you should just skip a year and go to 43.
Or stay 41 twice. And then jump to 43. Okay, Sally, tell them, where's it come from?
Hitchhiker's Guide to the Galaxy.
Right. A classic series. Agreed, Sally?
I still have to read the book called Life, the Universe, and Everything.
Oh, okay. Oh, you have fun. Yes, Terence.
It's worth actually checking out the number 42's Wikipedia page, because Douglas Adams was actually referring to a great many different things. 42 is an interesting number.
Evidently, the one about it being, did you say, Rosie, it was Japanese or Chinese?
Japanese.
So in Japanese, it means death. So I guess you
Yeah.
could have a whole lot of fun with that. Fun's the right word. No. So one last one of these. Yes, we've got time for it. This one, they have a lamina, which is basically just a name for a very thin piece. And in this lamina, I can't shade it, but it's basically very dark here, and then it gets lighter and lighter to the end, right? So you can imagine it's vertically scaled. So it's dark on this side and pale on that side. And we are measuring the density of the light by using that function, right? So you can imagine this. And what you're going to be asked to do here is, we don't have time. We are going to, when we come in next time, I just realized my watch, I should have paid more attention. This question is going to take a fair chunk of time to do, and I don't want to start it or rush through it because it's important, but we're going to find the center of mass. Now, what I can show you is what it would look like if this rectangle had the same density or the same light or whatever you want to call it, the same density. Would you agree that the center of mass would be the center of the shape? Right. Now, if you put a density function on it like this kind, couldn't you have an object where it's much thicker at this side and less thick at that side? So imagine that. If you were doing an object like that, because there's more weight on the right-hand side than the left-hand side, it wouldn't be surprising, would it, that if the center of mass would move more to the right to do that. Now, centers of mass are very important things to know in construction, amongst other things. If you're building a bridge, don't you want the center of mass to be in the center of the bridge, in the center of the road? Because that's the most stable place that you could have it. Now, it might be, if you're doing a ship, let's do a ship. If you're doing a ship, where is the best place for stability for the center of a mass of a ship to be?
Bottom of the hull.
As low as you can get. There would be the perfect place. If you have, let's put some structure on it. If you end up having your center of mass much higher, don't you have the instability of it could keel over to one side or the other, right? It could flip over if wind hits it in one way, right? If you want a building to have a really stable structure, right? One of these guys. Where do you want the center of mass to be? Right. You want it in the center and as low down as you can make it. So shouldn't you build all the heavy stuff? Your air can, if you could at least, all the pipe work, anything that's going to cause weight, shouldn't you build it low down in your ship or low down in your building as well? If you have it far too high and wind comes along, because aren't buildings very much like big sails, can't you get that horrible, the building moves? And there is a little bit of flexibility in buildings, right? They can move a little bit without falling apart, but you don't want them to move a lot, right? So if you're building anything, I have seen buildings like this, and I do not know what got into the guy, and I'm exaggerating it, but there's a building that looks like this. There's probably one in America as well. It's deliberately tilted.
Looks like a very exaggerated Leaning Tower of Pisa.
Right, and it looks architecturally quite weird and that's probably why they did it. It'd be a miracle to me if that is structurally sound. They can get away with it in places like London because we don't get huge 90-mile-an-hour winds, right? And we don't get earthquakes, and we don't get all sorts of things that might make it work. But if you have an object and its center of gravity is outside the building, isn't that building wanted to fall over? Even if it's inside the building and it's here, isn't it still probably going to try and fall over, especially if the wind's pointing in a direction that's encouraging that movement? So maybe a lot of architects should look into centers of mass. I wish Tim was here, because he could probably tell you that center of mass is very important on a crane. Don't you want it really low down if you've got a big crane? Otherwise, the crane will just fall over if you're not careful.
It's visually important too. I mean, when you look at a well-designed building that has a well-placed center of mass, it actually looks symmetrical, more symmetrical to the outside observer. It looks better.
It's pleasing to the eye. I don't, there's a lot of people out there, I think, who want to be different because square boxes are boring. And so they build some really weird shapes. Isn't the one in California that's sinking?
Yeah, meanwhile, they want to do all of these weird shapes, but what do they all study and gush about? Classical architecture that uses the golden ratio.
Okay, guys, say bye-bye and nice talking to you, but time to move on. You'll see the mechanics of how to get center of mass. There's a lot of work in it, as I said, and I don't have time. That's why we kind of did this. But at least, have I convinced you center of mass is cool? Right. Okay. Terence, how was homework going?
When we're done here, getting back on stuff.
Okay.
Don't get COVID. You won't think for a week.
I've had COVID. I also had the vaccination and caught it after that. I then gave it to my wife, who didn't have a vaccination. So the people that tell me that unvaccinated are the danger obviously didn't experience what I experienced.
Everybody in my household is vaccinated. We still got it. I'm going to tell you, as the person in the household who actually got their booster, I've had the mildest symptoms. Okay.
I've been told that. Yeah, and I understand that's very likely to be true.
I bet these other people have important stuff too. You have a good day, sir.
Okay, bye-bye, guys.
So long, and thanks for all the
Come on.
fish.
Come on, guys, say bye-bye, unless you get a question, Sally. No,
So
Brendan?
long, and thanks for all the fish.
all the fish? Where?
We were
don't-
talking about Hitchhiker's Guide, so I had to make another reference.
Oh, I wasn't on that one. Do you remember the reference about all the people that they put on the spaceship that were considered useless, like phone people who clean phones? No.
I don't know if I've gotten to the book with that reference. I've only
Oh,
read
okay.
The Restaurant at the End of the Universe.
Okay. Oh, yeah, that is, if you watch, there's a British series that was made, TV series, 6 episodes. Go hunting for it online. It's really good, really funny. So if you want to kind of get the whole, obviously it condenses the books into just 6 episodes, but it's really good.
Have a good rest of your day. I'll see you tomorrow.
You are right. I get Brendan and Rosie. Have we got any questions, or am I out?
I got a question.
Okay, what you got?
Is cumulative charge sort of like finding the average value of a function?
If you took the cumulative charge and then divided it by the area, it would be the average charge.